Yeah, somehow I feel life is difficult. I mean, yeah. Okay, so welcome guys. So this is my field theory abstract algebra section. So I want to build a video about a field extension. So we will talk about a field extension, and should we go to the Galois theory? Oh, but in this video I just the introduction. Yeah, this is the first video. Okay, so this video let's talk about a field extension. Okay, so let's only talk about field, right? So everybody knows a field. So field is a commutative ring with identity. So let's say this is R, and every non-zero element has inverse. Okay. So the ideal example are basically the rationals, real numbers, a complex number, also a finite field. Also, yeah, finite field. And now there are more field. Okay, so field. When I was undergrad, that I learned about this theory. I somehow I think field is hard to constrain. But once I learned the field theory, I learned this kind of field and understand that actually there are lots of fields. Okay. Okay, say that the extension. So extension. Well, some smart guy like to write f k. Okay, so if k is a field, and f is a subfield. So f is the same operations, the product and the addition as a subfield. Then if f is also field, then f is called a subfield. Of k. Okay, so yeah. Okay, or okay, but this has a consequence that you see k is a vector space over f, right? Because any element in k can be addition, and then you can times c, which is c is in f, right? And satisfy the 10 axioms of the vector space. So if you don't know about what's a vector space, then you should go to my linear algebra video list. By the way, I will also build a. Oh, by the way, I usually will follow the Hurston. So basically, it's a textbook that I think is easy to follow. Okay, so the dimension of k over f that the people write as a kf. Yeah, this is the notation, or okay. Or some people like to write as some people like it's kf, right? Just say that k is a field extension over f. Okay, so let's talk about the first theorem. Very easy. So if L is an extension of K and K is an extension of F, such that this is finite. So finite means the dimension is finite, right? Finite, then L over F will be L over K, K over F. Okay. Okay, so this proof is a trivial, so I don't want to. It's not so difficult. So this is M. Let's say this is M. This is N. Right, so that means this has basis. So let's say V1, Vm, V1 up to Vm is a basis of, so these are basis in all the element in L, right? Such that all the other element in L can be linear combination in K. Okay, and then you can write this is W1, Wn will be the K over F, right? Combine these two. Easy to check that Vi, Wj, where I from 1 to 2 to m, and the j from 1 to 2 to n is a basis. Okay, so it's a basis. Okay, check by yourself. Okay, so, okay. I mean, you can follow a textbook, but this is just a easy proof. So I don't want to prove. Okay. Okay, but then let's talk about the corollary. Corollary. The corollary says that if L is a finite extension of F, and the K is a subfield of L, which contains F. So basically, K is a subfield contains F. Then you always have a KF divides LF. right? By basically just follow this. Okay. Okay, so let's definition. So this definition is very important because we will use it in the future. Let's somehow I don't like the color red. It's a it's a little bit tricky. So let's using a careful okay, so if alpha belongs to K is say to be algebraic over F. If there exists element alpha 0, alpha n in F such that alpha 0 a so let's say A. So A is if A belongs to K, said to be algebraic over F. Then there exists some 0 up to n in F such that alpha 0 a n plus alpha 1 a n minus 1 plus alpha n, which is 0. Yeah, basically it's just the algebraic equation, right? Okay, so let's talk about the example. So this example is also it's also easy, right? So for example, square root of 2 is algebraic over Q, right? Because x squared minus 2 is a root, right? And the coefficients in coefficient is in rational, right? So also you can check that square 3 is also and the 3 this, and also I, right, is algebraic over Q because x plus 1 is 0, right? So this is called algebraic overfill. Okay, so let's talk about result. Okay, so let's talk about theorem. So this theorem is important. So A belongs to K is algebraic over F. If and only if F of A is a finite extension. Okay, so let me explain what is F adjoint A. So F adjoint A means that you take all the polynomial and put in A such that this polynomial P of X belongs to F of X. Yeah, so basically you just take all the polynomial in the last coefficient and put A in it. So for example, the Q adjoint the square root of 2 is basically A0 plus A1 square root of 2, A2 square root of 2 square, where up to AN square root of 2n such that all A0, A1, AN are just rationals. And then you know that the square root of 2 square is just 2, right? So you can write as this. Right, so this is the 2-dimensional. So Q's, so this is a 2-dimensional vector space over Q. Okay, so from this you get this. Okay, but this is just some example. Okay, so I just want to say F is a finite extension, A is algebraic over F. Okay, so let's see we prove this. So if FA is a finite extension, right, that means F of A, F, let's say this is M. Okay, so you can collect 1A squared up to AM, right? Because this M, so you have M minus 1. So they must be linear dependent. So this is dependent. So that means you can find an AI, alpha I, I from 0 to M, such as 0. Okay, so that means it's algebraic. So algebraic means that it has the polynomial roots. It will become some roots of polynomial. Okay, so that means just a small remark. So for example, if you ask about, so pi and e are not algebraic over Q. Okay, so if they are not algebraic, then people call it transcendental. So people say that pi and e are basically transcendental extension over over K. Over Q. Okay, so how about this part? So this part we hope to show that if A is algebraic over F, then the FA is a finite. F at joint A is a finite extension. How to do this? Okay, so let's say A is algebraic over F. A is algebraic over F. Then let's see, right? So let's see, if A is algebraic over F, then by assumption A satisfies non-zero polynomial f of x, right? So let's say P of x is the smallest degree, right? It's the smallest degree such that the P of A equals 0. So basically the smallest degree such that it can eat A. Okay, so we first claim that the P of x is irreducible over F. Okay, now this is easy, right? If P of x can be written as f of x times g of x, where they are both in polynomial in field f of x, and if it's reducible, it means that the degree of f greater than 1 and the degree of g greater than 1, right? Then that means you can, but you get P of 0 is 0, right? So either f of a is 0 or g of a is 0. Right, but that means you can just use f of g, which is replace p, right? But the f and g both have the degree less than p. I mean, either one of them will degree less than p, right? So which is a contradiction. So P of x must be irreducible. So irreducible means that the P of x cannot be written as the product of the two of the polynomial such that their degree is both greater or equal to 1. Okay, so now so now we will already claim that this is irreducible. Oh, okay. Okay, so let's let's see. Okay, so let's see. Let's now we already get that P of x is irreducible, right? But what we need to show is that what you need to show is if R is algebraic, we need to say f of a is finite extension. Okay, so we somehow don't know. Okay, so somehow we need to show f of adjoint a is a finite extension. Right, but I already said that I got some irreducible polynomial such that P of a is 0, right? So now I can construct a homomorphism called psi, right, from f of x into f of a, and this is simple, right? Just somebody give you f of h of x, right? Just map into h of a. Okay, so phi is a homomorphism as a field, and then you can ask about the kernel. So what's the kernel? So kernel psi means that you take the polynomial in f of x such that you put a is 0. Okay, but I know that the P of a is 0 and the h of a is P of a is irreducible, right? So h of a must be the P of a, right? It's the product of P of a. It's must has the P of a. Okay. Okay, so yeah, so you from here that you can check that that you can let PV to be the ideal generated by P. Okay, so you can check that if you let f your original f of x, the quotient is P, right? So this is you can since P is irreducible, so P is irreducible will lead to V is a maximum ideal. So this will make this to be a field. It's a field. Commutative ring divides commutative ring quotient the maximum ideal will become a field. Okay, so right, so this quotient, right, by the isomorphism theorem, this quotient actually this is just V, right? So this quotient will isomorphic to the image, right? Just by image of this psi, right? Icon this f of x, just the image. Okay. Okay, but by this definition, right? This f adjoint a is basically this is just surjective, right? Because h of x must be can be comes from f of x, right? So which tell you that this must be f of a. Right, so now I say that the f adjoint a just be v of x quotient this maximum ideal generated by p. Okay, but now you know. Okay, so now you notice that so now f adjoint a will be f of x v, right? So this v is just the irreducible polynomial generate this ideal. Okay, so you come from here that you know that this is the finite dimensional. This is a polynomial, right? So up to some order, it must repeat, right? So it tell you that f of a is a finite dimensional. It's finite dimensional. Okay, so we finish the proof, but we also show that the dimension of this will be just the degree of the irreducible polynomial, right? So the dimension f over f, f of a over f, will be the same as the degree of p of x. Okay, so this is somehow a little bit abstract. Let's say some examples. So for example, q at joint square root of 2 is a dimension 2, right? This dimension is 2. So q at joint of 2 by this will same as you take the q of x and the modulo x squared minus 2, right? So modulo the ideal generated by the irreducible polynomial. And the q at the joint 3 square root of 2 will isomorphic to q of x generated by x squared minus 2. Okay, but there is a tricky part, which is really tricky. Tricky part is that if you start from other roots of this guy, for example, you start from 3 square root of 2 times this omega, right? So this omega is a minus 1 plus the square root of 3i divided 2. Okay, so this guy will still isomorphic to these two, right? But now the key is that these two are they are the same field, right? But if you embed those two in R, they are not the same. So here okay, so here is a tricky part. There's a little bit. Let me just wait for the whiteboard. Okay, so what I want to say is that if you ask this field is isomorphic to this one, right? Because the irreducible polynomial of this 3 square root of 2 will be this, right? And also if you but another roots, and so x squared minus 2 has 3 roots, right? One is a square root of 2, sorry, 3 roots of 3 roots 2, and then 3 roots 2 times omega 3 roots 2 times omega squared, where omega is minus 1 plus the square root of 3 I divided by 2, right? So these guys still isomorphic to this. Right, but the key is that these two fields are not the same if you embed both layer in R, right? So because in the rational field, this Q3 square root of 2 must is some field or rational field, but this is not because it contains the imaginary part. So which tell you that these two fields are not the same if you embed both in R, but they are all isomorphic to the this. Okay, so this is the things that we will talk with, which is a separable. This is not a separable extension. Yeah. Okay. Yeah, so this is the final result, which is very important. If you want to ask what is the adjoint of an element A in F, then you just ask about what is the degree of the irreducible polynomial such that what's smallest the degree of irreducible polynomial such that the P of A is 0. Okay. Okay. So yeah, let's maybe let's say okay. So let's give a definition. So definition is that A belongs to K is to be algebraic of degree n. So there's a degree n here over F. So if A satisfied P of X in F of X, so polynomial with the field in F, so satisfy the P of A is 0. So if there exists the P of X belongs to F of X, such a P of A is 0, and the P is a degree n. So and I should say the n need to be choose the smallest. Okay. So no other no lower degree. Yeah, and then we prove the results that and then we prove the result basically tell you that F of A F degree will be okay. So theorem: if A B are algebraic over F, then A plus B, A times B, A divisible by if B is non-zero, and A minus B are in are algebraic. Okay, so which tell you that if you take two algebraic number, which their sum will be algebraic, times will be algebraic, divided by algebraic, A minus B algebraic. So it tell you that all algebraic number over F forms a field. Yeah, so this is basically what? Algebraic closure, right? Yeah, algebraic closure. Okay, so proof is simple, right? Because let's say the A, right? Let's say F of A has the sorry, F of A F has degree n, right? And the F of B F has degree n. And I want to ask that what is FA at joint B, right? FA at joint B F will be just F of A at joint A times F at joint A F. And then this is just some finite number, right? And then this is also a finite number, right? Because this is just less than yeah. So now now we need to we hope to we want to understand why this is why this is finite, right? But understand that this guy is F. Let me see how to say this. Right. Okay. So you know that we need to ask why F at joint A B F, right? So you can let's see. So maybe let's do this. So let's define TF of FA, which is degree. Let's say this is degree M, right? And then we know that the B is algebraic. B is algebraic over F of degree n. Okay, so this is what we have now. Okay, so let's talk. So W is T of B, right? So we know that WF basically just the F A at joint B F. We want to compute this. It's F A at joint B and F of A, right? It's the same as Y, just right? So this. Okay, so this is at most. So this is the first term is at most M, right? This is at most N. Okay, the reason is that this guy this guy is less than M. Let's see. The reason is that B is so So B is algebraic. Oh, this is M, right? So this is M, and then this is less than N. The reason is that B is algebraic degree N over F, and so obviously algebraic degree at most N over T. Okay, so because now you increase the field, right? You increase the field. So you can write this as a F A B, right? So in original F, you at most need a degree. You need degree N to satisfy, but now you increase you larger the field, right? So the degree should at most still M, right? So this is still finite. Okay, so once you did know this is finite, that means it must be algebraic. So the proof is done. Because it's finite, so it must be algebraic, right? So so all these are forms of field. All this is just obvious. Okay, and at most, you prove that you prove all of these at most degree M times N. I mean you can do the general. So yeah, although we all need to prove the two element, right? But you can easily generalize to the N element. Okay, so definition: if all element in F is algebraic, so basically if you take somebody give you a field, right? So, and over all the element over each ground field is algebraic. This is called the algebraic extension. Okay. So algebraic extension are not necessarily finite extension. But what we prove that if any A is algebraic, if A is algebraic extension over F, then the F adjoint A is a finite extension. But I don't say that the algebraic extension is necessarily a finite extension because the algebraic extension contains lots of, right? So there's a but yeah, there. So I know that all the finite extension, all the finite, all are yeah. So it's not necessary. There is a condition. There has a relationship. Okay, so theorem: if L is a extension of K, which is algebraic, and the K is algebraic extension over F algebraic, then the L is a extension of F algebraic. Okay, so proof is basically you take this as such. You take U be element of L, and then we need to show that the U satisfy the polynomial F. Okay, so let's say you get this xn sigma x minus 1 sigma n, where by this is algebraic, right? So sigma 1 up to sigma n are in K. Okay, but we know that K is algebraic, right? So K is algebraic over F, right? That means sigma 1 can be written as what? Can be written as some polynomial of F, right? So some polynomial in coefficient n F. So sigma 1 satisfies some polynomial in F. Okay, so by construction, you know that you can let M, right? You can let M to be F sigma 1, sigma 2. So you add a joint all the number, right? In M. So M is finite extension because all these are finite extension, right? Because they are algebraic. So M is finite extension. Okay, so M is finite extension, right? But now your U, right? Your U belongs to this, right? Your U is your U satisfies this property, so your U belongs to it, and the M is finite extension. So your U belongs to this. So U is algebraic over F, right? Because the algebraic extension for the single element which is algebraic over a field which is finite for U, which is a finite extension over some field which is must be algebraic. Okay, so if an element is algebraic extension, if an element is algebraic over some base field, then it adjoint must be a finite extension. Okay, so algebraic over algebraic is algebraic. Okay, so yeah, that's it. So that's the complex number is said to be algebraic number is its algebraic overfield of rational number. Okay, so that's the final definition. So algebraic number, which is people like to give a research, which is a very active algebraic number, is algebraic. I should say the algebraic number is a subfield complex number such that it's algebraic over Q. Okay, so algebra, yeah. So basically, satisfy the actually satisfy the polynomial with rational coefficient. Okay, that's it. See you guys in the next videos.